Welcome to Calculus. Today we will investigate integrating by completing the square. We'll take a look at three examples. Our first example is the integration of 1 over x squared plus 4x plus 5 dx. In order to recognize what type of integration this is, we really need to focus our attention on the denominator, x squared plus 4x plus 5. And I want to rewrite that as the sum or the difference of two squares. The strategy that I want to use to do that is completing the square from algebra. So what I'm going to do is I'm just going to bring the denominator over here to the right. And I want to complete the square so that its form shows that structure of something squared plus or minus something squared. So to do so, what I'll do is I'll separate the first two terms, this x squared and the plus 4x, from the constant 5. And what I want to do is I want to create a new constant so that I can factor this trinomial. And the way that I find that constant is I go to the b term, which in this case is 4, and I divide it by 2 and then raise it to the power of 2. So 4 divided by 2 is going to be 2. And then if I square all that, 2 squared is going to be 4. So I'm going to add 4 in that gap. Now I need to represent the fact that that 4 is something that I've incorporated. And it needs to balance out. So I need to have a minus 4, which I'll combine with my existing constant plus 5. The upshot of all that manipulation is my ability now to factor this x squared plus 4x plus 4. It's going to factor as a perfect square, so it's x plus 2 squared. And then I'm going to add up the two constants. 5 minus 4 is going to be plus 1. And that's equivalent, this x plus 2 squared plus 1, to my original x squared plus 4x plus 5. Once I've got that, I want to replace the denominator of the integrand here with the completed the square form. So I'm going to substitute that in. Now the advantage of writing it in that format is that I have several basic integration rules that have a format of a squared plus u squared or so forth in the denominator. So the one that we're looking for just now that would match this format is going to be this rule. So it's the integration. In fact, we'll write it here to the side just so we can see it. Of 1 over, in fact, we'll put du here in the numerator. So it's du over a squared plus u squared has the integration of 1 over a times arctangent or inverse tangent of u over a plus c. Now I probably do need to rearrange this x squared plus 2 and plus 1 so that it's matching my format here of a squared plus u squared. So I'm just going to flip this over. Let me grab my eraser there. I'll put 1 first plus x plus 2 squared. I'm just inverting that addition. Now I do that because it helps me identify my parts. This one would correspond to the a squared in my rule. And so if a squared is 1, the square root of 1 is just 1. So that's my a. My u squared is x plus 2 squared. So square root of that's just going to be u equals x plus 2. And this gives me a way that I can really quickly evaluate this integral. This is now 1 over a is 1, times arctangent or inverse tangent of u, which is x plus 2, over the 1 plus c. And just to clean that up, that's going to be simplified to arctangent of x plus 2 plus c. And that finalizes the integration for this first example. So again, just to recap, we use completing the square so that we can recognize a form in our given integration so that we can match it with an established basic integration rule. And this one happened to match up with the arctangent. Our second example is this one that involves a radical in the denominator. So this is the integration of 1 over the square root of 8 plus 2x minus x squared dx. So again, I want to start off by taking the quadratic that in this case is within the radical and completing the square for that. So I'm going to bring it to the side and I'm going to put the quadratic term first. So negative x squared plus 2x plus 8. And again, I want to complete the square. Recall, before I can do that process, I need to make sure that this coefficient in front of the quadratic term is positive 1. So in that case, it's negative. What I need to do is factor the negative out first. So I'm going to factor negative 1, and what that leaves me is positive x squared minus 2x, leave a space, minus 8. So I've left my 2 spaces so that I can complete the square. So recall, I take the b term, negative 2 divided by 2, and square it. And that's going to give me plus 1. And then I need to also subtract 1 to keep the balance. So for this example, we've got negative 1 times x. This will factor this x squared minus 2x plus 1 factors as x minus 1 squared, and then minus 9. And if I run that negative back through, that's going to give me positive 9 minus x minus 1 squared. So that's what I'm going to substitute in for this original quadratic. So it's going to be the integration of 1 over the square root of 9 minus x minus 1 squared dx. So once I've got it into that kind of completed the square format, I want to again compare it to some established basic integration rules. The one we saw in our first example involved arctangent. This one would match with a different rule. So this rule is going to be the integration of du over the square root. So it's got to involve the radical in the denominator of a squared minus u squared. And what that's going to equal is arc sine of u over a plus c. So a lot of the work here goes into just rewriting the integrand. Once you've got it rewritten, you just want to identify your parts. So this a squared, again, a is a constant, u is a function. So a squared is going to be our 9. If I take the square root of 9, a is going to be 3. This is important that that's a minus sign. It's got to match the sign. So it's minus, and then my u squared I can identify as x minus 1 squared. So my u is going to be x minus 1. And once I have those parts identified, I can just fill in into my rule here. This is going to be equal to arc sine or inverse sine of u over a. So u is x minus 1 over a was 3 plus c. And again, that completes the integration. Just as with our first example, most of the work is getting my integrand to look like the established basic integration rule. Our third example here involves a radical in the denominator plus an extra term out front, x plus 1. I want to identify the part that I want to complete the square with, and that's again this quadratic, x squared plus 2x minus 3. So I want to take that to the side, and we'll complete the square. So x squared plus 2x minus 3. I'm going to take my b term plus 2, divide it by 2, and square it. That's going to give me 1. So I'm going to add 1 and subtract 1. Again, I just keeping the balance there. I can factor that first x squared plus 2x plus 1, that quadratic is x plus 1 squared. And then minus 3 minus 1 is minus 4. So for this example, what we're able to do is then identify, well, first of all, let's substitute this back in. So it's going to be the integration of 1 over x plus 1 times the square root of x plus 1 squared minus 4 dx. So I do need to notice that I've got this x plus 1 matches that factor that was out front in the denominator. So again, I want to look for a pre-established basic integration rule. And this one is going to look like this. The integration of du over u times the square root of u squared minus a squared is going to equal 1 over a times arcsecant of the absolute value of u over a plus c. So we just want to check and see if we've got the parts that are established here. So my u squared, I'm going to check that one first, is x plus 1 squared. So that means if I take the square root, u is going to be x plus 1. Well, I'm in luck because I needed that u repeated out front, and that's exactly what I've got there. U is x plus 1. My a squared is going to be the 4. So a itself, if I take square root of 4, a is going to be 2. And again, I've got it into the pattern. Now I just need to substitute those values for u and a into the established rule. We'll integrate. So this is going to be 1 over a, or 1 over 2. We'd established that a equals 2. Arcsecant, inverse secant, of the absolute value of u, which is x plus 1, over again my 2, which is a, plus c. And that, again, completes the integration. Thank you for joining for this investigation of integrating by completing the square. See you soon.